Okay, let's continue on this chapter about ergodicity, chapter 4. So recall last time, from the last lecture, first of all, ergodicity means that f minus 1 equals E implies that mu of E equals 0 or 1. Okay, that's the definition of ergodicity, and we have seen that it has a lot of how to say equivalents. Like you can say that invariant functions are constant almost everywhere, and yeah, we have a bunch of equivalence definition that we can use. And remember, we have seen that circle rotations are theta are ergodic for theta irrational with respect to Lebesgue, okay? Theta. Okay. And remember, last time we have also seen a scheme on how to prove that when you have full branch expanding map plus bounded distortion, this also implies that Lebesgue is ergodic. And remember, Lebesgue is not necessarily invariant for full branch expanding map unless you have linear branches, not necessarily invariant. Okay, Lebesgue is not necessarily invariant, but what happens in these kind of systems is that the invariant measure will be absolutely continuous with respect to Lebesgue, and remember this property that if mu1 is absolutely continuous with respect to mu2 and mu2 is ergodic, so if you have this, then mu2 ergodic implies mu1 also is ergodic. So this is really a way to see that full branch expanding map, the invariant measure you get is ergodic. And I ask you to check these exercises for the Gauss map. The Gauss map, which and also, 10x mod 1 is the easiest example you can see. Like for a full branch map, the branches are linear and the invariant measure is Lebesgue. I just give 10x mod 1. For this one, if you remember, we have the invariant measure that is given by d mu x equals 1 over 1 plus x dx. That was the density we found using the Perron-Frobenius operator. Yeah, you can check that this guy has bounded distortion, and also, you have all these properties, then you have ergodicity. Yeah, so today we will study something different, a different type of dynamics, which is the Bernoulli shift. Bernoulli shifts. So this is a type of dynamical system that has a lot of application in many areas of sciences, but for our purpose, I will give an introduction of this for this Bernoulli shift, just using this type of map. I will say why it is important to study this dynamics. The next mod 1. To 0, 1. So if you have this dynamics, you can try to associate to each points in the interval with a sequence, and a sequence that that has information about the orbit. So given x in 0, 1, So you have f and x, the orbit of x, that is fx, f squared of x, and so on. So you can try to write a coding for this depending on a certain partition of this interval. So let's suppose that, you know, we want to associate to x a sequence of digits, you know, let me a0, a1, an, and so on. And what you do here is you define these guys, these digits, these numbers, depending on a partition. So what we know here is 2x mod 1 is doing something like this. So this is the dynamics. So we can have this interval. Okay, this is a half. Let's say this is I0 and this is I1. Okay, I don't include the boundaries, okay? This is just a measurable partition. Okay? So you can really, you know, follow these orbits by just seeing whether the nth iterate lands in this or this interval. So these guys will be defined as A0 is such that an is such that fn of x is in an. So these are the sequence of like 0 and 1. So this is in 0, 1 to the power n. Okay. But here you might have a problem because of, you know, when x is in these boundaries, or the image or some iterates of x lies on these boundaries. So you have to exclude those points to the set of points where you do your coding. So actually what I just write here, it gives an injection from, let's say 0, 1 x. You can write x as the space x. So this is small x. Okay, this is supposed to be little x. Okay, there's x, this space that I'm defining here, minus f minus n of 0, half, and 1. Like you're taking out these guys. This is countable. The point you're taking out is countable. 2, 0, 1 to the power n. And this is just defined like this. So you give x is given by a, let's call this map H. It takes A0, A1, AN, and so on. And AN is such that FNX is in. So you're just tracing the orbit depending on where you land with respect to this partition. So this is truly injective, right? Because this is injective, so H is injective. Because if not, you would have 2 points. Like if you have 2 points, let's say you have 2 points on this space x1, let's say you have xy on x. So these are different. So you see that there will be some n such that fn x minus fn y is greater than a half. Okay? Because this is this is 2n times, so roughly this is 2n times xy, and this grows. Okay? So it is injective. The claim is that this map is also a bijection. H is indeed a bijection. H is surjective. So why do we have that H is surjective here? Is if you give me a sequence, I can define the point that is associated to the sequence as follows. So indeed, so given A, that is A0, let's say AN. So sometimes I write this like this, okay? This is in 0, 1 to the power n. You can define x to be this guy. X is, you take I, A0, intersect with F minus 1, I, A1, intersect F minus 2, I, A2, and so on, intersect F minus N, I, AN. You keep going. And see that these are, when you stop at ends, you have an interval that is of order of 1 over, of size 1 over 2n. You can see that the limit is converging to a single point, okay? And this point satisfy h of x is this sequence, okay? So h is surjective. Now there is something important, like something interesting, why we want to, find a bijection from this space to this one, is in this space we have a dynamical system that is easy to understand in here, which is a shift map, or Bernoulli shift it would be called. So we write sigma as this space, 0, 1 to the power n. Okay, and yeah, so this is this space. So far, I just defined a set. I haven't put any topology, anything here. I will do that later. And in this space, you have a dynamical system, which is called the shift map. Sigma. What is this doing? It just takes sigma of an equals an plus 1. You're just shifting to the right. Okay. This is just saying that sigma of A0, A1, A2, and so on is A1, A2, so on. And there is something interesting, like how this is related to the previous dynamics. There is this fact that this guy conjugates the two dynamics, meaning H composed with F is 2x mod 1 equals sigma composed with H. Yeah, this is not difficult to check. You can just see that when you take fx, its orbit is just, just like going to the, shifting to the right. You just forget the first digit. You just erase this guy. That's what you get. So in some sense, you have this nice correspondence you have here, and you have your space x. You have f here, you have sigma here, and you have h, and you have this diagram that commutes. So this is just saying that h conjugates the two dynamics. which is sigma and f. Okay. Yeah. So now, why is this useful? Why is this useful? Because this dynamics is a priori is easy to understand. Like this is just a shift map. You know what are the fixed point here. Fixed point of this map is just, you know, you have 0, 0, 0, 0 or 1, 1, 1, 1, 1. You have periodic points. Periodic points are just the blocks that are repeated. You know, you form a sequence where you have a block of k digit that is just repeating. That is periodic points. So from here you can get a lot of information of f. But as you can see, there is a price to pay here, and the price is we lost type of regularity of the space, because this space is not nice. X is not like a nice space. Like you cannot put a differentiable structure here in X, because as you can see, it's not differentiable. The space X is not. You take out countably many points. But if you don't care much about differentiability, you just stick yourself to continuous properties like fixed points, like invariant measures, and some properties up to Holder regularity. This dynamics, this conjugation is very useful. Okay, and it's not only for 2x mod 1, by the way. You can do it for all the full branch maps. You can find your symbolic space, symbolic dynamics, and you might have more symbols, not only 0, 1, you might have finitely many symbols depending on the number of partition elements you have. Yeah, if you are countable, that's difficult to study, okay? A shifted space with countable symbols is difficult to study. But in general, even in higher dimensions, there are ways to like if you have heard of Anosov systems or uniform hyperbolic system, they have the same type of partition, which is called a Markov partition, that leads to the symbolic dynamics. And from the symbolic dynamics, you can study a lot of things like equilibrium states, like invariant measures, ergodic measures, you know, capture fixed point, prove that periodic points are dense, and so on. There are a lot of properties from Anosov diffeomorphism, like uniform hyperbolic system, that you can derive just by studying this dynamics. So I will start trying to put a structure on this space, okay? Because so far it's just like a set. I haven't even defined what is it like measurable? Does it have a sigma algebra, or is it a topological space? So I will put that formally here. Yeah. So the purpose of introducing in this lecture this shift maps is to study, you know, to get properties of the dynamical system F, which via this conjugation you have it. So this was just a motivation why we want to study these systems. So let's suppose that you have X be nu be a probability space Okay, so this will be the space of symbols. In this example, X is 0, 1, and nu is a measure on this, which will be a discrete measure. It just gives weights to 0 and 1, and B will be just a discrete sigma algebra. Okay, so we will have sigma is x to the power n. So this is a space of sequences. So we want to put like a sigma algebra or a definition So we will have a notion of cylinders which plays the same roles as open sets or intervals when you are in 0, 1. So we want to see when are two sequences nearby, for instance. Two sequences, like if you have A and B, just looking at this dynamics, 2x mod 1, when two sequences are nearby, that means that their pre-images are nearby. So two sequences nearby, it means that they have a first number of 1,000 or 100 digits that coincide, okay? So this is the motivation of the definition of cylinders. So we call cylinder of sigma a set of the form have M. So this is just a notation, okay? AM until M is bigger than N here, which is, this is a notation, okay? This is a set of sequences, xj, j in N. So this is on that space, sigma. Says that xj is in aj for j in between M and N. Okay, this is called a cylinder, where here, where ai's are, aj is in B. So there is a measurable set respect to B. In that example, B is a discrete topology, okay? So the product sigma algebra here that is defined on, so the product sigma algebra. So I will not prove the details here about why this is a sigma algebra and so on. You can find it in many textbooks. For instance, in the book that we are using for this course, the product sigma algebra in Bn is the sigma algebra defined by, generated by these cylinders, okay? By cylinders. Okay, I can just write it here. Okay, this is a sigma algebra, so it's just given by these cylinders. I mean, later on I will just, because this is general, okay? Later on I will just write when X is a finite set, that you can even define like the metric on this space, like this will be a metric space. But in general it is just like this. So there is also this theorem that I will not prove here because it's just measure theoretic result, so you can check it from the book in the appendix. I mean, they didn't prove it in the appendix, but they cited another theorem from another book. You can follow it from there. That exists a unique measure there is a unique measure mu on sigma Bn such that there is a unique measure that satisfies this property. The measure of this type of cylinder is just nu, the product from I equals M to J. I've been using J. I should be consistent with my notation. Of nu of Aj like this. So see that if you have seen product topology, like the Tikhonov topology, this is just along those lines, that open set in that topology are, you know, product of finitely many open set, and all remainings is the whole space. That's along the same line. When you define a cylinder, you just pick finite number of open sets, and everything else can run into, you know, X. So that's why when you take this measure, you should have taken the measure of all the product, but the other guy, there are measure 1, okay, probability space here. Like the other components of these cylinders, because they are countable, the others are just the whole space. That's why you just stick to these ones. Yeah, and this measure is denoted by nu n, okay, just a notation. Okay, that puts a sigma algebra and a measure on this space. But if you are in the case of finite symbols, like x is finite, if x is finite, like x, you can write it as A1 until AK. Okay, finite symbols, like in some cases where you have a final partition here, you can have 10 symbols, or, you know, then you can write this distance. So you can have a distance from sigma defined by, if you have x, y, two sequences, that is theta of n x y. For some, you know, you can fix any theta. So fix theta in 0, 1. Let's say theta is a half, for instance, where n here is defined is the largest number, n is the maximum of I, such that xj equals yj for j in between 0 and I. So this is just counting the number of digits that are the same for this sequence. So two sequences are nearby if they agree on a large set of digits, the large first digit, first n digits. So if n goes to infinity, you see that this goes to 0. So this defines a metric, and this also generates it defines a topology that is given by the cylinders, okay? So let's define definition. Okay, I'll shift map. So this is sigma. So it's the same definition over there. You take sigma of x0, x1, xn, and so on. This is just x1, x2. So this is just a simple dynamics. You are just moving to the right. Why this is simple? So there is this remark why this dynamics is so easy to study when you have these finitely many symbols, is that this measure is invariant. The measure that we define there is invariant. So remark, mu is sigma invariant. Yeah, the way to see this is just you can see what is sigma minus 1 of m of a cylinder like this. What is this? This is the set of x that is xj, just that. So what you have here is that the first component is something you don't fix, so it is xj plus 1 is in a j for j in between m and n. And a way to rewrite this is m plus 1 am an. And these two sets, they have the same measure, because the measure is just the product of these guys, because the first set is replaced by x, by the full space. So so you see that the measure of this is the same as the measure of that by the definition of the measure. So this dynamical system is called the Bernoulli shift. Sigma mu is called a Bernoulli shift. Okay, and we can see that actually. So you see, to prove ergodicity here, there's we use nothing. We just use the definition, because everything is set so that it is ergodic. The measure is defined so that it is invariant, so that it is invariant. Sorry, I haven't proved ergodicity. I'm sorry. I mean, to prove invariance, we don't pay any price for that. Okay, so let's see ergodicity. For that, let's prove this proposition. So if B and C are finite union of pairwise disjoint cylinders, then we have mu of B intersect sigma minus jc equals mu of B times mu of sigma minus jc. It is mu of B, mu of C. And this for J large enough, okay? For J, how large depends on B and C. For J large enough. If you think of this property, it is kind of similar to a property that we proved that was equivalent to ergodicity. Like we have seen that if the limit of this, when J goes to infinity, this implies ergodicity. Okay? So this is kind of what gives ergodicity. So let's prove this. So this is a finite union. So mu is finitely additive. So we can just think that B and C are cylinders to start with. So suppose B and C are cylinders, meaning B equals K BK BL and C equals M Cm Cn right. So if I go further with this property, I can see that sigma minus j of C is just M plus j with the same components here. So sigma minus j of C is just M plus j, and then AM AN. So the way to think of this is, this is a sequence, set of sequence where the first j guys is the whole space. You have x, j times, actually j plus m times, and then you have am times am plus 1 times an, and then x, and you keep going. Okay, so this is how you see these cylinders. And for j large enough, let's say j plus m is larger than L. So if you write B intersect sigma minus j, so for, let's write it here, for M plus j larger than L. So when you do intersection component wise. B intersect sigma minus 1 C. So you will have x. What did I do? Yeah, it's m. Yeah, so yeah, x. You will have it how many times? This will be j plus m minus. You will have this k times, and you will have b's. So b k. Oh, I should have said here k minus 1 times, sorry. So this is j plus minus 1, okay. Yeah. Bk times bk plus 1 times bl. And then here you would have x. How many times is, sorry, this is plus k, okay. This is how many times you would have x, because you have j plus m minus 1. So this is j plus, that's just L, yeah, sorry, j plus m minus 1 minus L times, and then you will have this guy. And so on. So you can see that if you take the measure, you will see that the measure is just the product of the measures. So you see that j greater than L minus m implies that mu of b intersect sigma minus jc equals mu of b, mu of c. Okay, because you just take products. What you have here will give mu of b. What you have here will give mu of c. Why did I write a's? Yeah, so I just, yeah, I changed C's to A's. Okay. So this should be C's. Okay. Sorry. This is C. Yeah, I should have chosen A and B instead of B and C. I should have chosen. Okay. All right. And since mu is finitely additive, is pairwise disjoint, you conclude for this proposition. So for the other case, we use that mu is finitely additive. Okay. Yeah. So yeah, and to prove ergodicity, what you do is you prove a proposition mu is ergodic. So the proof is just uses this proposition exactly as we did when we were proving that this is equivalent to ergodicity by choosing B equals C. First of all, you do it for proof. So what we want to prove is that sigma minus 1 of C of, let's say, A equals A implies that mu of A equals 0 or 1. So you first do it when A is a finite union of cylinders, finite union of disjoint cylinders, and you can use this property. What you would have is mu of A squared equals mu of A, which implies that mu of A is 0 or 1. In the other case, what you do is that if you take any, so for A being finite union of disjoint cylinders, there you can use the previous proposition to have this. For the other case, you can, so for general A, we find for every epsilon, find A epsilon, that is a finite union of cylinders, such that mu, the difference symmetric, is less than epsilon. Like this is just you take these points that are here, not here, and the point that are here, not here, their measure is less than epsilon. This is just saying that you can approximate this set with a set of cylinders, like finite union of cylinders, okay? It's the same thing that you apply, you approximate any set with intervals when you're set, and then you have, and then you use this, and then you can conclude by taking epsilon going to 0, okay? So let me get some. So I have two exercises that I want you to check. I have two exercises here. So exercise 1. Let's suppose that x is finite. So if x is finite, Then prove that the set of periodic orbits is dense. Then 1, prove that the set of periodic orbit is dense. In sigma. Okay. So for instance, when you prove this and you use the conjugation that I said before, you would conclude that your original dynamical system that you are studying, it has the periodic orbits are dense. And 2 is that it is transitive. It has a dense orbit, like that exists x naught in sigma, such that sigma n of x naught n is in n. This guy is the whole space. So this is transitive. Okay, this system is transitive. This is not difficult. Like this symbolic space is easy to study. When you just stick to, you see everything here is at the level of continuity. Okay, you take the closure with respect to the metric I defined there. So exercise 2. So prove that every infinite compact subset of sigma contains some non-periodic points. So this is again just because you know very well how periodic orbit look like in this space. So periodic orbits, yeah, periodic points. These are, you know, so periodic points is of this form. You can have x0, x1, xn, and you repeat this, x0, x1, xn, and so on, okay? And then you repeat this block, okay? This is periodic. Okay? And to solve this, you can just, you know, see that you can, it is compact. This is important. The phi is compact because the points you would construct, you just add all the possible digits you have from sequences that are on your compact set, and you use the metric to say that it is going to converge. It is converging to a point in the set. Okay. Yeah. So this is what I wanted to say about symbolic dynamics at this stage. So for the remaining of this lecture, I want to explain the Hopf argument that prove ergodicity for other type of systems, because if you see so far, I've been doing just expanding maps and circle rotation. So let's do Hopf argument. Okay, for this lecture, probably for today, I will just explain it for the simple case of a total of the simple maps, which is a matrix 2, 1, 1. And probably next lecture, I will explain how it works for general. So this is on T2. T2. Yeah. Why this is a dynamic of 722? Because you see that it leaves invariant, so A of Z2 is inside Z2, and that the determinant is 1, so this induces FA on T2, okay? Okay, and see that this guy has two eigenvalues. I think I have been talking about this map before. So so we have 2 lambda in lambda minus 1 are the 2 eigenvalues. So in this we want to prove that Lebesgue is ergodic. So this is what we are proving. Lebesgue is ergodic. Why is Lebesgue invariant here? Do we know why is Lebesgue invariant here for this simple guy? Determinant is 1, exactly, yeah. So Lebesgue is, yeah, we're proving Lebesgue is ergodic. So I forgot to say that here you can suppose that lambda is in 0, 1, okay? Because the determinant is 1, so you have 2 eigenvalues. One is in 0, 1, and the other one is the inverse. Let me explain the Hopf argument, how it works in this simple case. So these 2 eigenvalues, they give rise to 2 eigenspaces. So E lambda and E lambda minus 1 are the eigenspaces, the corresponding eigenspaces. So this is what you have is, this is your torus here, and you have, this is E lambda, this is E lambda minus 1. Sometimes I like to write them in 2 colors. I wrote them orthogonal because they are orthogonal in this case here, in this example. Okay. They're like this. So these are lines, so they're like this, as like this, like this, like this, like this, and you keep going. Okay. By the way, it's you should see what these are irrational slopes. Do we see why? This slope is irrational. The slope is irrational. So, dynamical point of view, there are probably millions of ways to see it, but a dynamical way to see it is if the slope was rational, so this line will close up, okay? And if this line closes up, so what I would have, I would be on the torus here, like this. Sorry. And I have this line that is if this was going to close up, this is the picture you would have, okay? This is a picture you would have. But what is the property of this eigenspace? This eigenspace has the property that if I apply FA, let's say Fna of a piece of this curve, let's say of C is just a piece of this curve. C is just a piece of this curve. The length of this guy will be like of the order of lambda to the n times the length of C, right? Because you can see it here, it is an eigenspace, so it maps like this. So if this whole curve was closing up, you would say that you would see an arbitrarily small curve that is closed. And that is impossible. It's impossible to see arbitrarily small piece here. So this is a curve that is going around this torus. If it was a closed curve, so if the slope was rational, by this property, lambda is in between 0 and 1, you would see that for n large enough, you will see a closed curve here. And closed curve that of arbitrarily small length, you can see you cannot have it on the torus. I mean, that is not I would say null homotopic. Like this is not null homotopic, okay? Because the only way to have it would be, to have a curve that is null homotopic. But this is is not null homotopic. This curve you would have is not null homotopic because it's going around. I mean, it generates, with this guy and this guy, they generate the fundamental group of the torus, so you don't have, that is null homotopic. So that's how you get the contradiction. That's why this guy is dense, okay? This guy is dense. This curve doesn't close up, it just goes around. For the same reason also you would have this. So for this guy, let's write it here. Okay. And so on. So this is how these two eigenspaces, they look like on the torus. So when you want to prove ergodicity, so for this picture, this gives me what we call two foliations. I have two foliations. So this gives stable and unstable foliations. So if you don't know what this means, it's just, at every, I have WS and WU, that is defined at every point. Okay, because at every point I have these two eigenspaces. In here, they are like straight lines, easy. Okay, but probably next lecture I will explain what are the problems you get in the general setting, like when the system is not like a linear system as here. So you have these two transversal foliations. Here they are orthogonal because but what is needed is just transversal, okay? So to prove ergodicity, it is enough to prove that the time averages are constant. So enough are constant almost everywhere, enough to prove that time averages are constant. So for that, let's write phi plus. So we take let C from T2 to R be a continuous function. Okay, and let's define phi plus to be the limit when n goes to infinity of 1 over n, the sum of phi composed with f j equals 0 to n minus 1. Why am I allowed here to write limit? Why do we have this limit here? Somebody knows? Why do we have the limit here? So this is FA, this is the dynamical system that we have here. And also I will define phi minus f minus j of a. Why do we have these limits? And I mean, do we have them? Do we have them at every point? Do we have them at least for some points? And why? Somebody knows? Yes, because of Birkhoff, we have Lebesgue is invariant. So you have this exists for almost every x. For Lebesgue, almost every x. I don't know if we have done this exercise, but we should have done, if we did not do it, that if your dynamical system is invertible, these two, they coincide. These two functions, they coincide Lebesgue almost everywhere, if you are invertible. But here, the main argument why it is called Hopf is what I'm going to write here. So Hopf, it tells you that this function is constant on stable manifold. So stable manifold are the blue curves here. Unstable are the red curves here. So there is this lemma that phi plus equals constant on WSX. So if you pick a point, phi plus is constant along the stable leaves of X. Again, this is a dense set. Okay? If I pick X is 0, 1, so this lemma is telling you that this function is constant for all points on this guy. This is actually why I was, at some parts in the lecture, I was saying that when you study this dynamical system, the stable manifold, you can really think of it as one point. Because if you are interested in the future they, they are going to behave like nicely when you apply a potential. So let's prove this. So let Y be a point on WSX. By the way, what I'm doing here, it holds for all linear toral automorphism, okay? That is hyperbolic. Hyperbolic means that you don't have eigenvalue 1, and yeah. If you have a point here, so if you write phi plus so already, I mean, you know, this is, Lebesgue tells you that it exists for almost every point. But this tells you that if it exists at one point on the leaf, it exists for all the other points on that same leaf, okay? So what is behind this lemma is that at least there is one point where you can apply Birkhoff there. Because, see that this leaf has zero measure when you look at it in the two-dimensional space, okay? WS, Lebesgue of WS is 0, okay? Because this is a curve. This is a line in the two-dimensional, okay? Because this is two-dimensional, okay? Okay? But I will be a little bit loose when I write here. What I could write is just really the sum here, this sum 1 over n, j equals 0, n minus 1, phi composed fj x minus phi composed with fj y. Okay. Now what happened is, for j large enough, so let's split this into two parts. J equals 0, sum n of this quantity plus the sum j equals n plus 1 to infinity of phi composed with fjx minus phi composed with fjy. So these 2 points are nearby. By how much? By, you know, lambda j to the power x. So distance between fjx and, so let me write it here. Distance between fjx, fjy is less than, actually it is equal. I'm here on this simple case. It is lambda to the j times the distance between x and y. Okay. If I were not on this simple case, you know, I would do something different, but let's stick to this case. And for j greater than, so this is less than lambda n plus 1, distance between x, y, for j greater than n plus 1. And phi is continuous, and you are on a compact set, so it is uniformly continuous. So that means that for every epsilon positive, there exists delta, such that distance between x and y less than delta implies phi x, okay, z1, z2, phi z1, z2, sorry, this guy will be less than epsilon. So if you choose n delta, you can choose n, you fix an epsilon, you can choose n such that the distance is less than delta, and you would have this whole thing will be less than epsilon. There is 1 over n, okay? Oh, sorry. This is n minus 1, okay? This n is less than that 1. That's not very good notation, but yeah. Small n is bigger than big N. Let's stick to that. Yeah, so what I'm saying is that this whole thing will be less than epsilon, and this will go to 0 as n goes to infinity. Okay, so what you would have is 1 over n you know, I think I'm being a little bit not careful here. What did I mean? Ah, yes, this is okay. What I say is here, I could just remove D because I'm on R. I can just do this. That's what I was looking for. Yes. J of y is less than this fixed quantity, 1 over n. The thumb j equals 0. So this n will depend on epsilon plus epsilon. And this, as n goes to infinity, this goes to 0 because you fix epsilon. N goes to, so this is as n goes to infinity. So you would have that this is constant. So this is really the main part of Hopf argument. Like points in the future, you can think of them as just one point. Like all the stable manifold, you can just think of it as one point when you're looking at evaluation on continuous potential. And similarly, phi minus is also constant on unstable manifolds. So similarly, phi minus equals constant on unstable manifolds. Okay, W U of x to be consistent. So now this is good. And here what let's see the picture we have here. So we have here one, so I'm going to write them as line. So this is x, points where you have points that is given by Birkhoff, where you have this limit exists. You have two guys. These two unstable manifold, stable manifold might not come from the same point. Okay? And you have transversally unstable that is doing like this. So from this lemma, let's see that here phi plus equals C1 is a constant, okay? On this set. So this is W1, WS1, sorry, and this is WS2. The goal is to say that these two constants are the same. So here phi plus is a different constant. C2, I mean a priori different, but we're going to prove that they are the same. And here also I have, how do you have it? I have phi minus equals C3. This is just Birkhoff and Hopf, this thing here. Why do we have two stable manifold for which phi plus exists? Is just because it exists almost everywhere. You know, it has to be at least two, because one stable doesn't have full measure. Okay, one stable manifold doesn't have full measure. So these two are different stable manifolds. Like I'm saying that they don't come from the same. You know, I'm saying that those two lines, it's not like, because these blue lines I draw here, they come from the same stable manifold. But those two blues are not the same, okay? So this is a part where, in general, one needs what is called absolute continuity of these foliations. I will say, maybe next lecture I will say what that means. So from Birkhoff, what you have is, so here I have at this point, let's say this is a point x where you start with, and it says a point y here. Y here. Let's call this guy x prime and this guy y prime. So here what you see is that phi plus is the same here and here. So that is Hopf. So phi plus of x equals phi plus of x prime. Okay? But now you can see that there is a full measure set for which these two limits they exist. And yeah, we should have done, I don't know if you have done this exercise. I think we haven't done it, that these two limits, they are the same. Okay? These two limits, they are like the same when they exist, okay, at the same point. So this is that argument which I like to call Hopf, this lemma here, and this is phi minus of x prime. This is Birkhoff, okay? Birkhoff and something else. I will say it later. This guy is again phi minus of y prime. This is Hopf, okay, that lemma. And this, by Birkhoff, this is phi plus at y. This is Birkhoff. So I should explain better this. It's not only Birkhoff, it uses the fact that when you, so this part here is not so exactly Birkhoff. It's using the fact that when you can decompose Lebesgue, so Lebesgue m dm can be written as dms times dmu. You can decompose your Lebesgue measure into measures unstable and measures unstable. It's just like a Fubini type of theorem here that you have. And each of them here is just Lebesgue measure on the leaf. Each of them is Lebesgue measure on the leaf here. Okay? So this is like a Fubini type of results. Okay? And then, so a full Lebesgue measure here is product of full measures here. Okay? Product of these two Lebesgue measure when restricted to the leaves. Okay? Restricted to the leaves. So here, this is what guarantees that you can find this x prime. You can find this x prime so that phi minus is phi plus, because this measure you can decompose it into stable and unstable, into the stable and unstable leaves, so that those restriction of the measure is just Lebesgue. It's just Lebesgue, okay? And yeah, so this is what gives the existence of x prime. So this gives x prime such that you have phi plus of x prime equals phi minus of x prime okay, and this y prime here is also tricky. Okay, to get this y prime, you use what is called absolute continuity of these like unstable leaves, like so. So what? Let me tell what would prevent what we are saying here to hold. Like if you have something like you have two foliations like this, and the other one, you know, is doing something singular, like this. Like it maps this positive measure set to zero measure set, so you won't be able to find this y prime. Okay, this y prime is just given also by the fact that you have this decomposition. Okay, same for y prime. So what I will roughly explain for the next lecture is this. I will explain roughly this part, like how you get x prime and y prime, okay, for which you have this property here, for which you can apply Birkhoff. This one is like is the Hopf, and this is absolute continuity of the foliation. So in general, this is what you need when you have a uniform hyperbolic system to prove that your measure, okay, it's not necessarily Lebesgue, but some measure that makes sense, that if you decompose it, you have absolute continuity. You can use Birkhoff. Here, the Hopf, you get it from the hyperbolicity. So this is basically the general scheme of Hopf argument to prove ergodicity for general systems. So I will stop here for today's lecture. In next lecture, I will try to spend maybe half an hour explaining the Hopf argument, and then we move to the other chapter here. So I will stop here.